How can we do that? So about lecture 4, and then lecture 3, and you are super.
Welcome to video number 22 in fluid mechanics. So this is the last video in section 7. And what we're going to be doing in this video is we're going to be looking at applications of these principles. So we're going to be applying lift and drag specifically to auto racing. And what I'm going to do is I'm going to tell the story of Chaparral Cars, which happened in the 1960s, because that's sort of widely regarded as like the first time we had a focused effort to use downforce on racing vehicles. And it's really a lot of fun to look into this, and it really demonstrates this idea of engineering principles and applying what we learned to real world applications. So I want to start off in talking about auto racing, because sometimes auto racing gets a bit of a negative reputation. The idea that it's just a bunch of people going out, trying to go faster than one another, trying to beat one another. And the idea might be that there's no real purpose to it, or there's no real goal other than beating each other. But actually, the reality is we owe a lot of the innovations that we see on like normal commercial passenger vehicles to the racing industry. There were tons of things that they came up with that have made cars safer, more efficient. And so what happens here, what I think auto racing is it's a great excuse to use the human spirit. The idea that when you're challenged and when you're chasing something, the idea that you want to win and you want to make it better, it really drives people to innovate more. And we've seen this also in different kinds of frontiers, like when we were exploring the Earth, or now we're talking about going into space and looking at possibly bases on the moon or colonizing Mars. And so I really like to focus on these things because I think they bring out the best in our engineering spirit, and the idea that when there's a complication we need to overcome, or when we're challenged, there's more room for innovation in those spaces, I think. And so in looking at auto racing, I think that's one of those places where you get a lot of innovation. So the story of Chaparral Cars really centers around Jim Hall. And Jim Hall was from Texas originally. And in the 60s, cars were becoming more widespread and racing was becoming more popular in America. So he had developed a passion for racing at a young age. Now, his family was in the gas and oil business. So when he first went off to university at Caltech, he enrolled in geology. But he quickly found out that wasn't for him, and he switched over to mechanical engineering. And he made up all the courses that he needed to, and he realized he really had a passion for mechanical engineering in general. So I've got some great quotes from Jim Hall from an interview that he did, and I'll play them throughout this video because I think it'll be good to hear in his own words, just how strongly he feels about engineering and just how much of a difference it made in his life, especially in his racing career and the development of Chaparral Cars.
I don't think I would have been a success in my life, really, without my degree. I don't understand how people live without an engineering degree. I mean, you understand the world around you and how things work, and it really was important in my work. I think you can have a lot of fun with it if you get into the right vocation.
So after he graduated, he thought he had a job lined up at Chevrolet, but due to some layoffs and some problems they were having, it didn't come through. So he ended up, he'd been racing his brother's car a little bit, and he'd actually become a pretty good racer. And his brother had a connection with Carroll Shelby. So he actually went to work at a dealership that Carroll Shelby had selling race cars. And so they became friends, and actually Jim Hall showed that he was actually pretty good at driving these cars around and, demonstrating them for customers. And so that was sort of where he really sort of took that first step towards racing. And to set the stage at that time, so aerodynamics was viewed at that time as like a negative thing, as something you had to overcome. Basically, they were just trying to get the cars through the air, and the air was in the way, right? So they hadn't really pieced together yet that you could use that surrounding air as a tool. And to put this in context, without trying to be too negative, but Enzo Ferrari had a quote at the time that said, "Aerodynamics are for people who can't build engines." So that kind of encompasses what the viewpoint was at that time. Now, it turns out Ferrari didn't do that well for the next few years in racing. But of course, they eventually got back on track. And so it just shows the power that aerodynamics is going to have throughout the 60s, and specifically the things that Jim Hall's able to figure out. And so that's why I think this story is going to be really fun for us to see how you apply these principles of lift and drag and how they can make something like a race car so much better. So Jim Hall's brothers end up running the family oil business, and so that leaves him free to pursue racing. And a big part of this story too is his partner, Hap Sharp, because he ends up, as you'll see along the way, getting to know a lot of very influential people in racing. And a lot of this is the discussions they have, about cars and about improvements. It's a bit of a team effort as well, right? So one of the first things that him and Hap Sharp do is they buy some land and they have their own racetrack. It's called Rattlesnake Raceway. I'll show a picture of it here. And basically, this racetrack is instrumental in developing the race cars because it gives them the ability to go out and test all the changes they make immediately. And so this racetrack has a lot of very interesting features, and it plays a big part of our story as well. So I'll label a few things here. You can see that the workshops are right here. So it's really convenient access to the test track, right? They could just take it, scoot it down here and take it right to the test track. And so it gave them this incredible ability to immediately test all their innovative new designs. Up here, there's a skid pad. They had their own skid pad so they could learn about tires and camber and lots of different things. And another really interesting thing about this track, so they put a tightening radius right down here. It's something that they'd seen on a track in Mexico that they raced, and they found it really, really challenging to do, so they put it on their own racetrack. And you can see the radius actually gets smaller and smaller as you turn this corner here, because they wanted to learn how to do that well. So overall, just a really interesting track and made a big difference to the innovation and development of their cars.
It's a good part of the test track, and we did an awful lot of work here. This is the kind of thing that I think made our team more successful, as we were able to come out here and test just almost any day.
Now at this time, Jim Hall was trying a bunch of different things. So he was actually quite a good racer. He actually raced in Formula One for a little while, but he went over to Britain and he didn't really like it that much. So he came back, and he'd always kind of had in mind, especially from working on all these race cars, that he always kind of thought he could do it better. And he'd always kind of had this idea that he'd like to make a race car. So at one of the races, he was approached by Troutman and Barnes. And these guys wanted to build like a homemade American race car. So they recruited Jim Hall to help them with it. And it was a really interesting experience for him because the car wasn't that successful, in part because it was one of the final like front engine vehicles. But it gave him this experience where, as the engineer of the car, as the designer, he had a different perspective for the first time on racing cars. So I'll put it in Jim Hall's own words here. I have a quote from him that I'm going to read out, because this first car, it went on to be known as the Chaparral 1, but it was really the stepping stone for him to get into his own car development, and we'll see how engineering plays a role in that. So this was his quote. "Before that time, even though I had an engineering degree, I kind of thought, gosh, this car doesn't handle well. Why wasn't it built better? But with the Chaparral 1, there wasn't anybody to complain to. It remained up to me to make it work. That's where my first chassis development came. I was really teaching myself how to make a race car work, and I guess it was useful in that respect." And so we see he had like a shift of mindset, right? He used to just take the cars and treat them as like they were something that was given to him. He'd drive them and they were either bad or good. But now, as the engineer, he was in charge of that, right? And so when he was developing this car, he was actually test driving it and figuring out how to make it better. So he switched his perspective onto something that was like, it was his responsibility and he could make it better. He could improve these cars, right? And that shift in perspective is really important going forward here. Okay, now what's known as the Chaparral 2A now is where things really get interesting. So this was the first car that was really the first one he did from scratch. Okay, so one of the first things they did is to go from front engine now to what was known as mid-engine cars, right? And this, of course, makes a lot of sense. You move the engine to the back because that's where you want the weight, but that's also where the wheels are that you're going to be powering, right? So that's one of the first things they did in this car. Now, one of the first things that was really important to them was to have a rigid chassis. Okay, so they had these big American engines, and they learned that it was really important to have a rigid chassis. So they looked into a bunch of different materials, and they were also taking a bit of a different perspective at this time. They actually wanted to go lighter. So they knew this guy, they had been looking around some aircraft facilities, and they met this guy who was able to actually build them a fiberglass monocoque chassis. So they were one of the first ones to have this in their vehicle, and it made the vehicle really light. It was really rigid. And so this was one of the big steps forward for the Chaparral 2A. Now, of course, this came with some unexpected downsides too. So they'd taken the engine from the front and put it in the rear now. And they'd also lightened the vehicle with this fiberglass chassis. So you can probably guess what the first problems were on this vehicle. When the front is really light, okay, and they hadn't mastered aerodynamics yet, now you're getting a lot of front end lift. okay? And what's known as understeer. So when the front lifts off, okay, you get what's called understeer because the wheels aren't gripping the track the way you'd expect. So when you turn, it doesn't steer the way you would because the wheels are lifting off, right? Conversely, oversteer, which we'll talk a little bit about later, is when you're getting too much downforce at the front, okay? So now it oversteers. So when you turn, you expect a certain steer, but it oversteers. Okay, so understeer and oversteer, they're terms we're going to use throughout this video here. That just refers to the front being either too light or pushing down too much. Okay, so as they were testing the vehicle, and remember they have their own racetrack here, they figured out that there was too much lift at the front. So they put an air dam on it, and I'll show pictures here as well so you can see this. Okay, they put an air dam on it. Okay, so I'm showing here when the airflow is redirected upwards, the air dam actually had to push that air up and over. So the force that the air pushes on the air dam, equal and opposite, pushes down and backwards, right? And now I'll just show the two components of that. So that results in a drag force on the vehicle, but also a downforce on the vehicle, a downforce that you can control with the shape and size of the air dam. And you can see this keeps happening, right? So they have to solve a problem. So their problem was they had too much lift, right? And so to solve this problem, they learned to push down on the vehicle. But again, they're not thinking at this point of aerodynamics as being a tool they can use to improve like traction or lap times. They're just solving a problem, right? The vehicle was too light. And so it's interesting how these solutions to these problems are going to lead them into figuring out how they can use aerodynamics in a good way, right? And so what happened was they really had to kind of test and tweak this as well. And the first time they put this on, they had like tin snips basically, and they had to go and cut it to size because at first it worked too well and it pushed the front of the body down against the tires. Okay, so they actually had to cut it and tweak it and, get it to balance. Balance is a really important thing they learned as well, because now what happened was, I'm going to demonstrate it with this little Lego car here. So you can see, like, if you push down more at the front, right, what happens at the back is you're actually getting more lift at the back of the vehicle, right? So you got to remember, you have a rigid chassis now. So pushing down here actually can lift the back of the vehicle. You can see this in wind tunnels as well. Okay, when you do force measurements on it, if you change the downforce characteristics at the front, you can sometimes end up with the opposite effect at the back of the vehicle. Okay, so in pushing down here, they realized, well, now they need an equalization force at the back. Okay, so they need some downforce at the back, right? So they still have traction on those rear tires as well. Those are the tires that's driving the vehicle. So with all that they'd learned, they actually made a new version of the 2A between 63 and 65. And so I've shown the new one on the right here. So we can see at the front of the vehicle, they completely redesigned it now, knowing they not only want to prevent the lift at the front, but they want to actively push down on the vehicle. So they want more downforce. So we can see on these pictures of the car as well, they end up putting like a spoiler. Okay, so they sort of have this little like scoop type shape. And so what happens is as the air comes across and is again redirected upwards, right? So that air, instead of traveling flat now, it ends up pushing back down against the vehicle, right? And so that pushes the rear of the vehicle down as well. So you can actually get a balance now between the front and the rear of the vehicle pushing down against the tires more evenly. You need balance to get race car performance, right? And this is where they had an interesting partnership as well. So they ended up partnering with GM. And now, if you know what was happening in the 1960s, so GM had signed this agreement where they actually weren't allowed to get into racing. Okay, so what happened then was part of their sort of development team ended up working with Jim Hall and Chaparral Cars. And so they'd go down to Texas at his racetrack in the winter, and they developed a partnership where they would bring things like their new, automatic transmission that they could test, and they'd share ideas. And so it really meant that they could develop together. And of course, GM had a wind tunnel. And at first, that's actually what they believe led to this design where the front end lift was too high on the first Chaparral 2A, because they'd used apparently a wind tunnel that didn't have a moving ground plane. And so it didn't give them quite accurate enough results. And so that's why they ended up having to fix the front. But we'll see, right? That actually becomes a beneficial part of our story because they learn about how to push down on a vehicle, right? And this is going to lead to their future advances on the car as well. So one of the things they did along with this GM team that they had working with them, is they put gauges on the vehicle to test the pressure at different locations. And what they found was along the wheels here, they had a high pressure zone. So you'll notice the interesting design where they have all these openings that are cut out. So what they wanted to do was take that high pressure air, right, and let it come out so it was released from the wheel well there.
We measured the pressure on the underside of the fender and then on the top, and then we vented from the high pressure to the low pressure. All that produced a negative force on the car, which allowed it to grip the road better, and the car went faster and faster and faster. Now, when I say faster, I mean faster around the racetrack. We put a lot of drag on this car. It got slower on the straightaway, and so our next step was to build a car that had a lot of downforce on it, but didn't have the drag on the straightaway, and that's where we went from here.
Now, they were very successful in this vehicle. So one of the big wins they had was Sebring, and I'll share this story with you because it leads to another part of car development we're going to see later on. And so when they won Sebring is a long distance race. Okay, so it started to rain, and actually because they had this fiberglass monocoque, it ended up filling up with water. So this great story about how they were 5 laps ahead and they were deciding if they should keep running or not. And so they ended up, this vehicle won Sebring, but it filled up with water in the rain. So we'll see how that changes the designs of their vehicles later on as well. So the big lesson before we move on from the 2A is that in doing all this balancing of the lift forces on the car, Jim Hall figured out, especially because he was the driver, right? So we remember a big benefit here is like, he's the engineer, so he had a mechanical engineering degree. He's also the driver, because he's a great driver, and he's their test driver as well. So he takes the car around the track. He's also one of the team owners, right? So this combination is really powerful. And that's another lesson I think it's important to remember as an engineer, right? If you really go out there and you really participate in how these designs are implemented, that can really strengthen your design capability. Okay, so what he figured out on the 2A in driving it was that as they got more downforce, his lap times went down. And so he pieced together, right, that like a car that was perfectly neutral, where the lift and the downforce balanced, wasn't that great of a car. And he figured out the more downforce you had, the quicker it went. So in playing with this solution to solving the lift problem, he figured out, right, from testing it, that the downforce was actually beneficial. They could corner so much faster. They got all this traction and his lap times just went way down. So he was much, much faster with downforce. Now that he'd pieced that together, they could start to make some really quick, really competitive race cars by applying this downforce. And that's known, he says that's his biggest sort of contribution to the racing field, was this idea of using the downforce to improve the performance of the vehicles. So this is the 2C now. Now, one thing they did is they moved away from their fiberglass into aluminum. And they did that for really practical reasons, right? So firstly is it's a little bit lighter for the same rigidity level, but also it allows them to change it, right? With fiberglass, they just had to rely on their partner from the aerospace industry to make them these fiberglass chassis, right? And then there was nothing they could do to change it. Whereas with aluminum, they could modify it a bit more and change it. So this car now has an aluminum chassis, same kind of idea, very rigid, very light. But we'll see later on that leads to some issues in itself, right? So we've got to look at the design as a whole, and they kind of piece some things together with that. So another big thing they had on this vehicle was they had a really innovative automatic transmission that they were trying out for GM. And they realized this actually leads to some innovations as well, because it freed them from having the clutch pedal, right? So now we'll see later they could use their feet to do other things with the vehicle. What we can see if we look at the back of this vehicle is the first time they have a movable spoiler. So they're starting to piece together what we talk about in section 7 is when you're generating downforce, you're also generating drag, okay? Now, you definitely want the downforce to increase your speed and decrease your lap times, right? But in getting better cornering, okay, you want the downforce on the corners, but you don't want it on the straightaways. You don't want that drag on the straightaways, and you don't need the downforce on the straightaways. So if they have a movable spoiler now, on the straightaways, they can lift it, right, and allow the air to travel over to reduce the drag, okay? And on the corners, they can drop the spoiler, right? When they need that downforce, and then they can corner faster. So a movable spoiler was a really big thing. This gave them a lot of speed, right? On the racetrack, they could do really well in this car. So even though the 2C was really successful and they also won a lot of races with it, they realized, again, as engineers, they wanted to keep pushing forward. So there were more innovations to make, and there were some problems they wanted to solve as well. So the aluminum chassis proved to be a little bit too rigid, so it was uncomfortable. So they had to work on that. It also conducted heat, right? So it got very warm with the engine sitting on it. It would get very warm for the drivers. And also they started to realize, right? So everything we've seen so far in terms of downforce, like pushing down on the vehicle, is actually attached to the body itself, right? So when they push down on it, they're pushing like against the springs, against the suspension system. And so they realize that they're having to buy like very strong springs, okay? And a lot of these forces are being muted out by having to push against the springs on the vehicle. So that's something they also piece together that they have to solve now. And it's just becoming more and more evident that this downforce is a really positive thing for racing. So this is one of their big contributions, one of the biggest things they've figured out, right? Is how do we get more downforce, but how do we use it in a really effective way? So there's two things, right? How do you make sure there's not too much drag? Okay, but also, how do you prevent it from pushing against the suspension too much? And how do you actually get it to push down where you need it, which is in the wheels, right? So when working with this movable spoiler too, they'd also figured out some really advantageous things that will help them innovate as well. So what they figured out was to move the spoiler, right? It's actually kind of tricky because you're very busy when you're driving a race car, right? And you don't want to have to go too far. You've got a lot of things going on, okay? And so this is where having the automatic transmission really helped out because they could control the movable spoiler with a foot pedal. And that also makes it fail-safe as well, because if you have it naturally locked in the down position, right, so pushing down on the vehicle, then what happens is on a straightaway, when you're accelerating, right, and when you want the lower drag, you can push down the flap so it releases. Okay, so that's your low drag mode, but also your low downforce mode. And then what happens is the moment you need to brake coming into a corner, yet you lift that foot, right? So they're using 2 foot, like right foot for the accelerator, left foot for the brake. So now you lift that foot off of the pedal. So automatically the spoiler, comes down, right? The spoiler comes down back into its downforce mode. So that's the safe mode when you have to brake, okay? And so that makes it like a very clever system. And they go on to use this in some of their later designs. So that's another thing I'll point out as well in this video here is there's a lot of confusion about what's a spoiler and what's a wing, right? And so people use the two interchangeably, but they're really not. And so we see what we're calling a spoiler here, right, is actually part of the bodywork, okay? And it acts by just having the air come over it and they move the air off of it and that pushes down on the vehicle. Whereas a wing, okay, when we say a wing, that's actually a full-blown airfoil, okay, that's located normally up above the vehicle a little bit, so it gets the clean air, okay, and that actually acts like a wing where it generates downforce, okay, by the different flow over the top and bottom of the wing itself, right? So they're two very distinct things. A spoiler and a wing are different. So the Chaparral 2D is interesting. I want to take a quick look at it here because, again, as engineers, we can see some of the sort of very practical things we design. So if you'll notice, this was the car they used for their long distance races. And we can see what they've learned now from this versus their earlier 2A vehicle, right? You've probably all seen it by now. It has a roof on it, right? So that when it rains, it's not going to fill up with water, okay? It's also added the ram scoop at the back, okay? And that was a nice innovation because it takes that, again, it's another use of air over the vehicle, right? This is what Jim Hull as an engineer is capable of doing. So he takes the air over the vehicle, right? And when you take that high velocity air, okay, and slow it down, you get a high pressure. So the ram scoop's able to take that high pressure air, okay, and you now have high pressure air that you can feed down into your engine. And the big race that this car won was Nürburgring. So there was a distance race at the Nürburgring. And this car, that was kind of the big victory there. Actually, my dad is a huge fan of Chaparral. So anytime we talk about these cars, he always likes to talk about the big sort of victories they had because they were very successful at the time. So he was a huge fan of it. And that's part of the reason I got into it. And it's such a cool, story to show us lift and drag. right? So that's why I think sharing this story is really showing how we can apply and we can be innovative. And like, hopefully that's what you take home from this, is the way we can use this Section 7 material, and frankly, the material in the whole course, right, to make things really exciting, really innovative. Okay, so now we can move on to the 2E. And in some ways the 2F as well. And we can all see from looking at this, the really big thing this has is the wing, right? So this was the first introduction of the wing, and this is where they now needed to solve another problem. So I mentioned they were pushing down in the body of the vehicle. So this wing, for the first time, you can see how it's mounted. It pushes down right on the axle itself. So it pushes the wheels down directly, okay? It doesn't have to go through the springs. That was a big deal. That's, of course, nowadays how a lot of the racing cars are mounted. But at the time, this was a big deal. This was a really big innovation. The wing is also movable, and they took what they learned from the movable spoiler and they implemented that as well. So you had a pedal to control the wing as well. And again, it was fail-safe, because as you lifted your foot off the pedal, the wing's natural position was to drop down into its downforce mode, which is also its high drag mode, okay, as you hit the brake with your left foot. Okay, so as you came into the corner, it would automatically go into its downforce mode for more safety, so you could corner better. Now, with the movable wing came problems at the front again, because we remember you have to balance the vehicle. So if you have two modes on your wing, right, every time you flip into that high downforce mode, what happens is, again, you can get a lifting at the front. Okay, my little Lego car can show this for us. So if I push down at the front, right, that can result in lifting the front tires, okay, which is going to lead, again, to understeer. Okay, so they realized, right, that what you could do to balance that, to keep the car balanced in the corners, is to have something at the front, right, that also controlled the amount of downforce that was happening at the front while you were changing the downforce at the rear. And this is really clever how they did this. So we can see from this schematic that they have the air being redirected at the front, and as you take it in the front and release it out the hood, okay, that generates downforce as well. So what they could do was they could just close off that flap, right? So they could block it, okay, when they didn't want that air to generate the downforce at the front. And then you could release a flap that would let that air flow through when you needed more downforce at the front. And the way they controlled this was brilliant. So basically it was a passive system, okay? And you had this spring, so that it was really clever. The spring would be set in such a way so that if the velocity of the air was high enough, okay, that it would actually push against the spring, right? And it would release the flap so the air would just flow down. So if you were in the high speed mode, okay, and you didn't want that downforce, the flap would block it and redirect the air in another pathway, okay? And then as you slowed down, right, like you would coming into a corner, now you need the downforce mode, okay? So that spring would actually release then, and you'd have the air passing up into its downforce mode. So you could just really cleverly calibrate a spring, right? And then again, you're using the force of the air. So at the high speed, it can push the spring, and at the low speed, the spring is up and allows the air to travel through. It's really genius design, you know, to have this controllable downforce system so that you could have different modes on your vehicle, whether you were on the straightaway or you were cornering. Increases your speed that much more. And I'll show some shots of this. This was really quite a legendary vehicle. So you have races where he's the only one out there with a wing, and they were so fast with this car. Another thing they did, another kind of neat thing we can see on the schematic here, is they moved the radiators backwards, okay? And that helps with some of their heat problems, but also it moves the weight more towards the rear, and they can actually use the air in these side pods here, okay, to come over the radiator, which is cooling the engine, right? So when he first brought it to the track, the story is that a lot of people laughed at him, but as he puts it, and again, maybe let him put it in his own words here.
When he first showed up at the racetrack, a lot of guys laughed at the wing, but I noticed that the knowledgeable people didn't. Bruce McLaren was down laying underneath, looking back up in there to see where those struts went. And Dan Gurney was standing there too. So the guys that really knew, they weren't laughing.
And by the end of this race, people were pretty scared of this car. It was so fast, okay? And so like he knew he really had something at this point. But sort of unfortunately what happened is they tried to implement this on other cars, specifically F1 tried to do this, and they had some fairly bad accidents where the struts either broke or fell off and people were complaining that they couldn't see and things like that. So they ended up banning them at the end of that season. So he couldn't actually use them anymore. You know, this incredible innovation ended up getting banned. And he was quite upset with a few different races, like the Can-Am series was supposed to be sort of wide open racing where you could come with these great innovative ideas. And they kind of let him down as well. So it was an interesting part of the story there that he was actually like so innovative, so far ahead of his time, that they ended up banning this great idea. But, you know, we'll see. He had some more ideas in his back pocket at that point. So he keeps pushing the innovation forward on this car. Now, the Chaparral 2H, as it's known, I'd like to skip this. I know when he gets interviewed, he doesn't like talking about this car too much as well. It was one of those ideas where, like, it was a great idea on paper, you know, and it could have worked well in execution, but he'd had a fairly bad accident and he wasn't driving anymore at this point. So when he wasn't the driver or the test driver, he couldn't actually tweak the designs as well. And we can see that was a weakness for this vehicle. He hired John Surtees, right? Really famous, a really good driver. And he just wasn't comfortable with the car. So they sadly ended up having to take this great design, which was basically like a streamlined design, like make the whole car like an inverted wing. And that avoids having, you know, the raised wing, which became banned, right? But they ended up having to tack like a spoiler on the back and a bunch of other things to get it to work. And Surtees wasn't comfortable sitting down in it, so they had to put a pod over his head. A lot of those things made it not work, but basically it just shows like not everything always works the way you want it to, right? But he still pushed forward, and we'll see coming up is one of his biggest ideas here. So the Chaparral 2J is really interesting. Sometimes you'll hear it referred to as the sucker car. And what he had pieced together is because the wing, you had to pay a drag penalty basically, right? And this, we've talked about this a lot in section 7, is when you have the lift or the downforce generated by a wing, you suffer because it's up there blocking the air as well, so you get increased drag. And so he managed to piece together that if he could use the road or the ground to pull the vehicle down, you might not have to pay as big of a drag penalty. And so this was another aha moment, which we now refer to as ground effects. This is one of the first ground effects cars that we're going to see. So the way he did it was very clever. He managed to make a skirt out of Lexan, okay? So he actually puts these two fans on the back, as we can see in the picture here, and they're powered by a snowmobile engine, actually. And so he actually just sucks all the air out of this, and because it's skirted, he creates a low pressure zone that pulls the vehicle down against the road. And so now you get this tremendous downforce, okay? But you don't have quite as bad of a drag penalty. You still have a bit of a drag penalty, right? But it's not as bad. And so you're getting incredible downforce without paying that penalty. So these cars were really fast. He actually managed to convince Jackie Stewart to drive it at one point. And as Jackie Stewart got out in this race, he easily set the fastest lap. The car didn't finish that race, but they showed that this was like a really serious idea. You also created this really neat scenario where your wing generates downforce, but it's dependent on your speed, right? So you actually have to kind of be careful. You need to carry enough speed into the corner to continue to have that downforce. So there's a bit of a challenge there when your downforces are dependent on your speed, but in the sucker car, they're not dependent at all. You actually just control your downforce, right? With those snowmobile engines sucking the air out. So it's not a function of your speed anymore, right? So you've now created this other benefit, is that you can basically essentially corner as fast as you want, okay? And there's some quotes from Jim Hall as well on this. Essentially, you could corner so fast, the driver could black out. Okay, so there was a limiting point, was actually now the driver's like physical ability to take the corner quickly. That's how incredible this car is.
And that translates to 2,000 pounds of downforce. The car weighs about 2,000 pounds, so by just tweaking it a little, we could have driven it on the ceiling or on the wall.
Now the challenges with this car, so of course if those fans fail, right, so the snowmobile engines are controlling fans that suck the air out, right, and generate the downforce under the vehicle. If those fans fail though, now you've got a serious issue, because now your steering becomes a big problem, right? Because the car is designed to have that suction. So that's one big concern there, is if the fans fail, your steering is going to really suffer. Also, some people complain that there were stones or debris being blown out by these fans behind the car, which made it a little bit dangerous. And there's an interesting benefit we know from taking this course, right, is because those fans are pushing air out the back, you're actually getting a degree of thrust, right? And Jim Hall said that if the engines totally fail in this car, you could still run those fans and you get the car to go at about 31 miles an hour still. You could actually drive off those fans because the thrust from the fans could push the vehicle. So that's kind of interesting as well. And so this car is really the culmination of, you know, all the ideas that he had where, you know, you needed downforce for speed, but you paid a drag penalty. And now that he had these ground effects, right, everything was coming together nicely to make this really fast race car. But again, the FIA stepped in, and some of the rules makers stepped in and basically said this car was banned, you know, and, you know, they found a bit of a loophole in saying that, you know, it was movable aerodynamic devices, which weren't allowed on vehicles because the skirts could be moved and because the fans were moving. So they banned it that way, which was really unfortunate because, you know, it was really an innovative idea at the time, but maybe even a little bit too ahead of its time. Now at this point for Jim Hall, he'd used a lot of his best ideas. He'd really proven that downforce could be really powerful, and he'd had a ton of success at Chaparral Cars. At this point, they'd banned, you know, his Wing and his sucker car, and there wasn't a lot to do at this point. So he took a break for a few years, but then he decided to come back into IndyCar racing. And so this is a great end to the story. He was very successful, and we see now he's able to use ground effects in a different way. So he's using passive ground effects. And I can show in this video that I have of him, basic idea is the Bernoulli principle, right? That we've seen. If you get velocity to go up, your pressure goes down, right? Under the vehicle. And this was an extremely successful car.
The way this car makes more downforce is through a channel on the bottom of the car where the air flows. And it all happens in the side pods, not in the middle. It happens underneath the radiator opening. That's the entry to the throat of a venturi, in effect, and then it exits out the back where you see the triangular shaped area. It expands to the exit. This is a venturi, and it uses the Bernoulli principle. So the low pressure is in the throat, and the throat is up here right in the center of the car, actually towards the rear, so that you put balanced downforce on the car. And the way you make the venturi is the shape of the car plus the road. And that's what makes the venturi shape, and then the downforce is provided by the low pressure underneath the car.
So they were able to win with this car. And again, it's a really happy ending to this idea that your engineering innovation can be used in so many ways. Once you really understand the principles, you know, governing these things, you can apply them, right, to make incredible innovative things. And so it was nice at the end of the story that they could come and have this really successful Indy car, and he was applying, you know, his ground effects, his downforce on this vehicle one last time to get this final success in. And we see, you know, a lot of these things are used today. So I want to talk about the DRS system in F1. That's an example of this where they sort of still limit the movable aerodynamics you can have on a vehicle, but the DRS system actually makes the races really exciting. So DRS stands for drag reduction system. I'll show a video of it here.
A device called the Drs Wing. It's the rear wing of the car, and they wanted to improve overtaking. You can use it anytime you like in practice and qualifying, but in the race you can only use it after the end of 2 laps and only if you're within a second of the car in front. So how does it work, Pat?
Well, firstly, we call it the DRS. DRS stands for drag reduction system. Everyone knows that the wing is here to produce downforce, but in doing so it also produces drag. It slows the car on the straight. The DRS is a device that allows part of the wing, the rear flap, to move. By moving, we don't get so much upwash from the wing, we don't get so much downforce, but more importantly, we don't get so much drag. So we can pick up 10 to 15 kilometers an hour of top speed just by making this movement. It's moved by this hydraulic actuator which moves the flap thus.
And that's again the idea of lift and drag, right? And how you have to pay, a penalty between your lift and drag. Okay, so I hope you enjoyed that. You can see how it really brings everything together here. We can see, the first time they thought about using downforce on a vehicle, how it came about. I just think it's an excellent example and something for us to keep in mind as you go through, your career and the rest of your degree here is when you challenge yourself and when you're solving challenging problems, you can come up with really innovative ideas, and don't give up on them, and know that these solutions can lead to other things, right? Solving problems can always lead to other innovations if you're out there looking for it and if you're really involved in the problem. And so I think that's what we've seen here. This lift and drag idea actually led to some incredible innovations on making cars way faster. And so this exciting thing is, I think, something we should focus on for engineers. And it's another way to think about pursuing challenges, like the idea that we could put a base on the moon or colonize Mars really gets the human spirit engaged, right? And we're solving more complicated problems. We're going to innovate more. And this is an area where engineers are really powerful. So I encourage you to look for things that you're passionate about, things that challenge you, okay? And then you can apply your engineering to make incredible innovations, right? And to find solutions that really help humankind move forward. Okay, so in summary, we looked at how you can apply the principles we learned in section 7, such as lift and drag on a racing vehicle, and how you have to think about things like balance and the difference between the penalties you pay between the lift and the drag. And it was a really nice way to sort of demonstrate how you can use these things in principle. We talked about innovation and how if you pursue things you're passionate about and things that challenge you, you can really make incredible designs. And as you solve problems, keep in mind that they can lead to other things. So that brings us to the end of section 7 here, at the end of video number 22. This also sort of wraps up the new material we've covered in the course. So that really brings everything to a nice close here. And I hope you've enjoyed it. And that's the end of video number 22.
Bye-bye. I'm done, Dada.